Hi, I'm Shehryar Sardar and this is my Physics 2211 Lab 1 Constant Velocity. Here's my table of contents with introduction, models, experiments, code, discussion, and conclusion. Starting with our purpose, we have two main goals: to observe an object moving in the same direction at a constant velocity, aka experiencing zero net force, and to compare predicted results from a computational model to observed results from real life. Fundamental physics principles. Newton's first law, the law of inertia. An object at rest will stay at rest, and an object in motion will stay in motion unless affected by an outside force. An object moving experiencing no outside force will continue to move at a constant velocity. Newton's second law, acceleration of object is proportional to the net force it experiences, which simplifies to F equals ma. Models. First off, we have average velocity, which is the change in position over the change in time. Second, we have velocity update, which can be derived from the Newton's second law, F equals ma, to find the final velocity. And same for position update, which we can use to find the final position. Here is the results preview comparing our predicted motion to our observed motion over time. Experiment. Procedure. For materials, we need a ruler, an object such as a card, which is our system, a flat level surface, our surroundings, and a camera. First, measure the length of the card. We will use this in the tracker. 2. Push the card to give it an initial velocity and let it roll. 3. Record the card moving in a straight line. Next, we have data collection via tracker. In the images on the left, we can see the length of the card and the direction of the positive x being in the direction of motion. In the table on the right, we can use the hand inputted input values for the position at a certain time frame. Next, there is the code. Let's start with the initial values. To get the initial value for position, we assume the object starts from the origin. However, the discrepancy can occur from manual input error in tracker. To get the initial value for velocity, we solve for the average velocity using the model from earlier and inputting the final position and time and initials from tracker, giving us around 0.45 meters a second. The next part of the code is to get the time values. Delta t we can pull straight from tracker. Then we have the loop. In the loop, there's three things we need to solve for: Fnet, the ball velocity, and ball position. Velocity and position, we can use the models from earlier for position and velocity update. For Fnet, since it's a computational model where we are assuming a perfect situation, we simply set it to the zero vector. Next, our results. On the left, you can see a position rest time and velocity rest time, which shows us that the velocity is constant for the whole duration. In the middle, there is a visual representation of the ball after it has moved to the right. And on the right, we have all the time values on the left and position values on the right in order. Moving on to a discussion. Our final results can be seen in the graph below. And the blue line shows our predicted position from the computational model, and the orange is the observed position from the tracker. The slight difference between these can be accounted due to manual input or possible sources of error, such as friction or air resistance in the observed model. Some other similarities between these is that the slope of it is relatively the same, which shows a constant velocity over time. Now for some discussion questions. If the x-axis was flipped, how would the data change? All the values and the position and velocity would be in the other direction, aka it would be negative. The overall motion would be the same, but all the changes and such would be in the other direction. Is the net force actually zero? In the observed model, it is not actually zero due to outside forces such as friction or air resistance slowing it down. What forces had to be added to reach zero net force? In the observational model, those forces would be the force of gravity acting downwards and the normal force acting upwards, which would cancel all the forces in the y direction. And the computational model doesn't include friction, so we can automatically set it to zero. In conclusion, this lab showed us how predicted and observed motion of a constant velocity in the same direction can be displayed using both live observation and input and computational models. Thank you for listening and have a good day.